So picture this. If you stood inside, a next-generation AI data center, and the cooling systems just suddenly failed.
Which is a terrifying thought, honestly.
Yep, right, a total nightmare. But if they failed, the silicon that's processing all your requests wouldn't just overheat and shut down nicely.
No, not at all.
Given the extreme thermal density of modern high-performance computing, those microchips would literally melt themselves into slag in a matter of seconds.
Yeah, it's a violent environment in there.
Exactly. We always talk about the cloud, right, as this weightless, ethereal concept. But the physical reality keeping it aloft for you is this violent, highly engineered thermodynamic battle.
It's basically a massive industrial plant.
It is. So today, we are pulling back the curtain on the multi-million-dollar synthetic plumbing that's keeping the AI revolution from, well, literally catching fire. Welcome to the deep dive.
Glad to be here.
Today, we were exploring the hidden liquid lifeblood of modern tech infrastructure. And our source for this is a really fascinating 2026 technical data sheet for a product called Supermicro coolant, specifically the SMC PG25-A.
Yeah, and this document really signaled a fundamental architectural shift in the industry.
How so?
Well, I mean, for decades, the high-performance computing industry relied on massive fans forcing chilled air over metal heat sinks. That was the gold standard.
Right, just blow cold air on it.
Exactly. But we have crossed this thermal threshold where air is just no longer physically capable of removing the heat generated by these latest AI accelerators.
It's just not dense enough to pull the heat away.
Right. So this data sheet, alongside the accompanying schematics for Supermicro's data center building block solutions, it outlines this massive transition to advanced synthetic liquid cooling.
Okay, let's unpack this. Because to really appreciate why a proprietary synthetic fluid is necessary in the first place, we have to grasp the sheer magnitude of the thermal crisis at the silicon level.
The problem starts right on the chip itself.
Yeah, and the datasheet specifies that this SMC PG25-A is engineered for, quote, high-density AI liquid cooling systems, and it's optimized for high heat flux.
That phrase, high heat flux, is key.
Right, and for those of you who track semiconductor roadmaps, thermal design power, or TDP, has been climbing like crazy.
Oh, absolutely skyrocketing.
We're looking at single GPUs pulling upwards of 1,000 watts now. But heat flux is the real metric of concern here, isn't it? We aren't just dealing with a lot of heat, we are dealing with a staggering concentration of heat.
The concentration is the existential threat, definitely. Because heat flux measures thermal energy transfer per unit of area.
Right.
It's typically expressed in watts per square centimeter. And, well, in older architectures, the heat generated by the transistors was spread out enough that the thermal resistance of air wasn't a bottleneck.
So you had a bigger physical footprint for the heat to escape from?
Exactly. You could just push more CFM cubic feet per minute of chilled air over a copper heat sink, and you could keep the silicon within its operating margins.
Just run the fans louder.
Yeah, exactly. Just make the room noisier. But as Dennard's scaling broke down, engineers just kept packing tens of billions of transistors into the exact same reticle limit of the silicon wafer.
So the physical space isn't growing, but the power is.
Right. The heat isn't just increasing, the density of that heat is increasing exponentially.
Which means the thermal boundary layer of air simply becomes an insulator at that point. Air just has a terrible specific heat capacity compared to liquid.
Precisely the issue.
Yeah.
I mean, if you attempt to air-cool a next-generation AI chip operating at maximum heat flux, the thermal resistance between the silicon, the integrated heat spreader, the thermal paste, and then the air, it's just too high.
The heat gets trapped.
Yeah, the heat cannot physically escape the silicon fast enough, regardless of how fast your fans are spinning. The junction temperature spikes, thermal throttling kicks in immediately.
And your performance tanks.
Exactly. And if the physical safeguards fail, the chip suffers catastrophic electromigration and physical destruction. It just burns itself out.
Wow. And this is where the source document highlights direct-to-chip liquid cooling.
Yes, the primary solution right now.
Now, I want to clarify the mechanics here for you, because moving to liquid introduces its own set of thermal resistance challenges. Are we bypassing the integrated heat spreader entirely here? Is this synthetic liquid coming into direct physical contact with the bare silicon die?
No,
Okay, so we're basically putting an ice pack directly on the AI's forehead, or is there still an intermediary block?
There's a block. We are not immersing the bare silicon die in this specific PG25A architecture. Immersion is a whole separate paradigm that some people are working on.
Right, like giant vats of boiling fluid.
Yeah, exactly. But when Supermicro refers to directed checks this context, they were describing a highly engineered cold plate system.
Okay, so how does that work?
Basically, a precision machine thermal interface, which is usually copper, is mounted completely flush against the silicon, and the internal geometry of that copper block is carved into thousands of microscopic channels.
Oh, wow, so tiny little rivers inside the metal.
Exactly. And the PG25A fluid is forced through these microchannels under immense pressure.
So the fluid is capturing the thermal load mere micrometers away from the heat source. By forcing the liquid through those microchannels, you're drastically increasing the surface area for heat transfer while taking advantage of liquid's vastly superior thermal conductivity compared to air.
That's it. And you are also forcing the fluid into a turbulent flow state, which is crucial.
Turbulent flow, why does that matter?
Well, in fluid dynamics, if a liquid moves too slowly or smoothly, which we call laminar flow, the fluid that is directly touching the hot copper heats up, and then it actually acts as an insulator for the rest of the liquid in the channel.
Oh, I see. So the liquid in the middle of the channel stays cool, but the edges are hot and the heat doesn't transfer efficiently?
Exactly. So by pushing it forcefully through these microchannels, you create turbulence. You are constantly breaking that thermal boundary layer and mixing the hot fluid at the edge with the cooler fluid in the center.
Maximizing the heat transfer coefficient. But pushing fluid aggressively through microscopic copper channels has to require immense mechanical effort. Which brings us directly to the physical properties of the SMC PG25A itself.
This is where the chemistry really matters.
Yeah, the datasheet places massive emphasis on its, quote, low viscosity formulation, claiming it delivers efficient heat transfer and stable flow performance even under demanding operating conditions.
What's fascinating here is how the kinematic viscosity of the fluid dictates the power usage effectiveness, or PUE, of the entire data center facility.
Right, because viscosity is basically just the measure of a fluid's internal resistance to flow, its internal friction, like trying to suck a really thick milkshake through a tiny straw versus just drinking a glass of water.
That's a perfect analogy. If the pump, your lungs in the milkshake example, has to work harder, that's wasted energy.
And in a massive hyperscale facility, we're talking about pumping tens of thousands of gallons of this coolant through miles of primary and secondary loops.
Miles and miles of it.
So if the fluid has a higher viscosity, like the milkshake, the mechanical pumps in the cooling distribution units have to work exponentially harder to maintain that turbulent flow we just talked about.
Right. And the relationship there is actually governed by the pump affinity laws. The power required by a pump scales with the cube of the flow rate, and it's highly dependent on the pressure drop across the system.
And forcing thick fluid through microscopic channels creates a massive pressure drop.
Exactly. A viscous fluid creates massive pressure drops. To overcome that, you need larger, higher wattage pumps. And in a facility operating thousands of AI server racks, the parasitic power draw of just the cooling pumps alone can measure in the megawatts.
Wow. So wasted pump energy equals massive electricity bills.
Massive. And a higher carbon footprint.
So shaving off a tiny percentage of the energy used just to move the coolant translates to huge operational savings. The chemical makeup of the coolant directly impacts the facility's bottom line. But wait, you say lower viscosity translates to massive energy savings. Isn't there a fundamental trade-off in fluid dynamics? Usually, if you formulate a chemical to be thinner, don't you risk lowering its specific heat capacity or maybe its boiling point?
Yes, that is a huge factor.
So how does PG25A manage to carry away enough heat if it's explicitly formulated to be thin and highly flowable?
That is the core engineering challenge Supermicro had to solve with this specific chemistry. I mean, water actually has a fantastic specific heat capacity and incredibly low viscosity.
So why not just use tap water?
Well, water makes a phenomenal baseline coolant from a pure physics standpoint.
Right.
But as we'll discuss in a minute, pure water is highly destructive to industrial metals and biological ecosystems.
Right.
So the PG25A is a synthetic propylene glycol-based formulation. Propylene glycol inherently have a higher viscosity than pure water and a slightly lower specific heat capacity.
So the chemical engineering goal here is to blend it. You introduce just enough propylene glycol and proprietary additives to achieve the necessary chemical protections without raising the kinematic viscosity so high that you ruin the pump efficiency.
Right, or destroy the fluid's ability to absorb the thermal energy. The low viscosity formulation mentioned in the datasheet means they've optimized the ratio.
Okay, so it's a very specific balance.
It is. They maintain a Reynolds number high enough for turbulent flow in the microchannels while keeping the pressure drop across the server rack within the strict tolerances of the CDUs.
Ensuring the pumps don't consume the very electricity the liquid cooling was supposed to save in the first place.
Exactly. It's a very delicate dance.
So you've optimized the fluid to rush through the system with minimal pump energy, carrying massive amounts of thermal energy away from the silicon. But moving warm fluid quickly through miles of metal pipes introduces a completely different and arguably more insidious set of problems.
Oh, definitely.
Which brings us to the chemical battlefield outlined in the text.
Because a fast-moving, thermally efficient fluid is completely useless if it is actively corroding the system from the inside out.
Here's where it gets really interesting. The datasheet promises, quote, comprehensive system protection, guaranteeing superior antibacterial performance to prevent biofouling.
That's a huge one.
And it also mentions multi-metal corrosion protection, specifically for copper, aluminum, and stainless steel. So let's tackle the biological threat first. Because we are talking about highly controlled, sterile-looking data centers, how does a bacterial infection become a threat to an AI supercomputer?
It really comes down to the environment we are creating inside that closed loop. I mean, we are taking a fluid, heating it up via the AI chips, and circulating it continuously.
It's warm and wet.
Yes. We are creating a perpetually warm liquid environment. That is the biological definition of an incubator.
Oh, wow.
Even in a closed system, if microscopic biological contaminants are present, honestly, they almost always are, they will find that warm environment highly conducive to reproduction.
And when they reproduce, they form biofilms. They just anchor themselves to the internal walls of the plumbing.
Exactly. And specifically, they love to anchor in areas of high heat and complex geometry.
Like the microchannels inside the copper cold plates.
Exactly. This is what the datasheet refers to as biofouling.
Which basically acts as a microscopic thermal blanket. The thermal conductivity of a bacterial biofilm has to be abysmal compared to copper or the coolant.
Oh, it's terrible. It totally insulates the metal.
So if a biofilm coats the inside of those microchannels, it doesn't matter how fast the fluid is moving or how low its viscosity is, the heat just can't bridge the gap between the copper and the fluid.
Right.
The thermal resistance spikes, the fluid passes right by without absorbing the heat, and the AI chip undergoes thermal runaway. It cooks itself.
It does. And furthermore, biofilms excrete highly acidic byproducts.
Oh, geez.
Yeah, so not only are they thermally insulating the silicon, they are actively eating away at the copper cold plate from the inside.
So the superior antibacterial performance of PG25-A isn't just some nice secondary feature.
No, it is an absolute operational requirement. The fluid must be highly biocidal to ensure that not a single microbial colony can take root in the system over years of continuous operation.
But the fluid can't just be a harsh biocide, right? Because it also has to play referee between all the different metals in the system.
That's the other side of the chemical coin.
Yeah, the source explicitly mentions protecting copper, aluminum, and stainless steel from corrosion. And anyone who has worked with mixed metals in plumbing or, automotive cooling knows about galvanic corrosion.
Wait, isn't it true that if you mix different metals in a liquid, they start eating each other like a battery?
That's exactly what happens. Galvanic corrosion is a severe threat in any multi-metal liquid cooling loop. You have dissimilar metals, say copper in the cold plates in the GPUs, and aluminum in the heat exchangers or the manifolds further down the line.
Right.
When you introduce a fluid that acts as an electrolyte connecting those two metals, you inadvertently create a crude galvanic cell, a battery. Because the metals have different anodic indices. They have completely different electrical potentials.
Yes. Electrons will naturally want to flow from the more anodic metal, which is usually the aluminum in this case, to the more cathodic metal, which is the copper.
Wow.
As the aluminum gives up electrons, it oxidizes. It literally dissolves into the fluid.
That sounds catastrophic.
It is. You end up with pitting in the aluminum components, massive structural weakening, and eventually a catastrophic leak.
And as that aluminum dissolves, the fluid fills up with microscopic metallic particulate, right? Which then acts like sandpaper on the impellers of the mechanical pumps, degrading the entire system's efficiency.
It ruins the pumps, it clogs the microchannels, it's a mess.
So how does PG25A prevent this? The datasheet mentions specific inhibitors. Are we talking about anodic and cathodic inhibitors that fundamentally alter the surface chemistry of the metals?
That is a standard mechanism in advanced coolants like this. The PG25A is engineered with very complex chemical inhibitors, often specialized azoles for copper, and silicates or organic acids for the aluminum.
Okay, and what do they do?
As the fluid circulates, these inhibitor molecules bond to the surface of the respective metals on a molecular level.
So they essentially form a microscopic monomolecular clear coat over the inside of the pipes and the cold plates?
Yes, exactly, a passivation layer. It is incredibly thin, so thin it does not negatively impact the thermal conductivity, but it acts as a physical and electrical barrier.
So it blocks the circuit?
Right. It prevents the electrolyte from reacting with the bare metal, neutralizing the electrical potential difference, and just halting the galvanic electron transfer entirely.
But that raises a really critical operational question for me. If these inhibitor molecules are constantly bonding to the metals to maintain that passivation layer, don't they eventually deplete?
They do.
Does the PG25A have a chemical half-life where the data center operators have to flush the entire system and replace it because the inhibitors are exhausted?
That is actually a primary maintenance concern for data center operators. While this specific datasheet doesn't outline the exact degradation rate, industrial coolants of this caliber are engineered for multi-year lifespans.
So they don't have to change it every few months.
No. The concentration of inhibitors is carefully balanced to provide long-term stability without altering the fluid's viscosity. Routine maintenance involves pulling small fluid samples to test the pH and the inhibitor concentration levels.
Just topping up the chemicals, basically.
Right, rather than flushing thousands of gallons of fluid preemptively.
Which really underscores the delicate balancing act this fluid is performing. It must be a lethal biocide to prevent fouling, it must chemically passivate mixed metals to prevent galvanic dissolution, and it must maintain a low kinematic viscosity for turbulent flow.
It's an engineering marvel, honestly.
It is, and yet there is a fourth vector of compatibility we have to consider, because the metal pipes aren't the only materials containing this fluid.
Right, we have to consider the elastomers.
Exactly. Moving to the compatibility and flexibility section of the document, Supermicro highlights that PG25A has exceptional compatibility with a broad spectrum of materials.
Yes.
Specifically citing plastics and elastomers, namely EDPM and silicone. In a facility with tens of thousands of connection points, the integrity of the O-rings and gaskets is arguably the single most critical point of failure.
It absolutely is. And if we connect this to the bigger picture, a single degraded O-ring in a server rack can cause a localized leak that shorts out hundreds of thousands of dollars of AI accelerators.
A tiny rubber ring taking down an AI model.
Exactly. So when we talk about elastomer compatibility, we are looking at how the chemical solvents in the coolant interact with the polymer chains of those rubber seals.
Because certain chemicals will cause polymers to swell, or they'll extract the plasticizers from the rubber, causing it to become brittle and crack.
Yeah, that happens a lot with incompatible fluids.
So if the coolant doesn't have this compatibility, your silicone seals dissolve, and suddenly you have hundreds of gallons of synthetic liquid pouring over millions of dollars of AI hardware.
Exactly. Or, conversely, it might harden. EPDM ethylene propylene diene monomer is a highly robust synthetic rubber used extensively in automotive and industrial cooling.
Very standard stuff.
Right. But if exposed to an incompatible hydrocarbon-based solvent, it completely loses its elasticity. And in a data center, thermal cycling is constant. The temperatures of the servers fluctuate wildly based on the computational load.
Like when they're training a model versus when it's idle.
Yeah, and the metal fittings actually expand and contract slightly with those temperature changes.
So the O-ring has to remain perfectly elastic to maintain the seal during that micro-expansion and contraction.
Yeah.
If the coolant has degraded the EPDM, making it brittle, the next time the system cools down and the metal contracts, the O-ring just fails to expand and fill the gap.
And you have a massive leak. The explicit mention of EPDM and silicone compatibility here really assures the infrastructure engineers that the chemical inhibitors and biocides we just discussed will not cross-react with the polymer chains of the seals.
The whole liquid ecosystem just must be deeply harmonious.
It has to be. Maintenance in an AI data center is just costly downtime. The fluid chemistry has to guarantee that the physical infrastructure remains largely untouched, set it and forget it, for years.
Well, this level of chemical precision brings up a massive logistical hurdle. I mean, we were talking about a highly engineered, perfectly balanced synthetic fluid, but a hyperscale AI data center isn't a small laboratory.
Hmm.
The volume of fluid required to cool megawatts of compute power is
It's hard
immense.
to even picture the scale.
Right, so how do you actually get this highly specialized, non-corrosive, antibacterial fluid into the data center safely in the first place?
Well, the supply specifications in the datasheet address this reality directly. They detail the fluid as a PG-based formulation, propylene glycol,
Oh.
and they heavily emphasize its low toxicity, classifying it as generally non-hazardous.
Which is a big deal for shipping.
A huge deal. This classification profoundly simplifies transportation, storage, handling, and regulatory compliance.
Yeah, the visual supply specs really hammer home the scale for you. We see a 20-liter jug, a 200-liter barrel drum, and finally, a massive 1,000-liter metal-caged IBC tote.
Those totes are huge.
We aren't just talking about a little bottle to top off your radiator. An IBC tote is the size of a small car. It requires a forklift just to move it. It suggests these facilities are taking delivery of this coolant by the literal ton.
Oh, absolutely by the ton.
Yeah.
If you calculate the thermal mass required for a facility pulling 50 or 100 megawatts of power.
Just staggering amounts of power.
Right. The primary and secondary cooling loops require a staggering volume of fluid just to fill the lines, let alone account for the expansion tanks and reservoirs. When you are dealing with thousands of liters of industrial chemicals, the NFPA hazard ratings and environmental regulations dictate your entire operational model.
This is where the choice of a propylene glycol base, rather than ethylene glycol, proves to be a masterstroke of logistics, doesn't it?
It really does.
Because ethylene glycol is the traditional base for automotive antifreeze. It's highly effective thermally, but it is acutely toxic to humans and animals. If a forklift operator accidentally punctures a 1,000-liter tote of ethylene glycol in a loading dock, you have a major hazardous materials emergency.
It would be a nightmare.
Yeah.
It would require immediate evacuation, specialized hazmat response teams, and severe environmental reporting to agencies like the EPA.
Right.
Because ethylene glycol can contaminate groundwater.
Right.
Propylene glycol, on the other hand, metabolizes completely differently. It is actually widely used in food processing and pharmaceuticals.
So it's basically safe.
Yeah. By engineering the PG25-A on a low-toxicity PG base, Supermicro effectively neutralizes the bureaucratic and environmental friction of scaling liquid cooling.
That phrase, regulatory compliance, in the datasheet is doing a lot of heavy lifting. I mean, data centers are already facing intense scrutiny from local municipalities just regarding their power and water consumption.
They're constantly under a microscope.
Right, so if these facilities were also stockpiling millions of liters of highly toxic chemicals, the zoning approvals and insurance premiums alone would grind AI expansion to a halt.
Exactly. Making it non-hazardous removes a massive friction point for scaling up this infrastructure quickly. The non-hazardous nature of the fluid allows facility technicians to perform routine maintenance, bleed lines, and swap out server nodes without wearing advanced personal protective equipment.
They don't need hazmat suits.
Right? They could just do their jobs.
Okay.
It changes the operational tempo of the entire data center. You solve the thermodynamic bottleneck with the physics of the fluid, but you solve the deployment bottleneck with the safety profile of the chemistry.
That is a fascinating way to look at it. So we've zoomed in on the fluid, its chemistry, we've explored the microscopic dynamics, the heat flux, the kinematic viscosity, the passivation layers preventing galvanic corrosion, and the elastomer compatibility.
We've covered the fluid itself pretty thoroughly.
And we've looked at the massive 1,000-liter IBC totes required to deliver it. Now, I want to step back and look at the macro architecture, because the fluid is basically useless without the massive physical machines that actually pump this 1,000 liters of fluid around the data center and reject the heat.
The mechanical heart and lungs of the system.
Exactly. This brings us to Supermicro's Data Center Building Block Solutions, or DCBBS.
Right. This is where we see the physical manifestation of the cooling strategy. The datasheet outlines a complete modular AI infrastructure, providing hardware that bridges the gap between those microscopic cold plates we talked about and the wider facility environment.
Yeah, the visual schematics in the source present a really fascinating array of hardware. There's the in-rack CDU, the in-row CDU, the L2A sidecar CDU, the rear door heat exchanger, and the massive outdoor dry cooler water cooling tower.
A lot of options.
So what does this all mean for the data center architect? It seems like they're presenting a highly modular, giant adult Lego set for AI. Depending on the size of your facility, you just snap together the exact cooling architecture you need.
That's exactly what it is.
Hmm.
Modularity is the only realistic way to manage the transition from air to liquid right now. Data centers are not monolithic.
Right? They come in all shapes and sizes.
Yeah, they have different floor loading limits, different ceiling heights, and different primary cooling loops. So the CDU, or cooling distribution unit, is the critical isolation barrier in this architecture.
Isolation barrier, meaning it separates the highly specialized PG25-A fluid in the server racks from whatever water system the building itself uses.
Exactly. A data center typically has a facility water system, or FWS, which might just be treated municipal water. You absolutely do not want that facility water flowing directly through the microscopic channels of your million-dollar AI chips.
Because it would clog them instantly.
Instantly. So the CDU sits between the two systems. It houses a massive plate heat exchanger. The specialized PG25A fluid, which we call the technology cooling system or TCS loop, circulates exclusively between the servers and the CDU.
Ah, I see.
Inside the CDU, the heat transfers across the metal plates from the PG25A into the facility water without the fluids ever actually mixing.
That makes perfect sense. It minimizes the volume of the really expensive PG25A you need to buy, and it totally isolates the delicate microchannels from any contaminants in the broader facility plumbing.
Exactly.
So the different types of CDUs, like in-rack, in-row, sidecar, they just represent different spatial configurations for this heat exchange process.
Yes. The choice depends entirely on the spatial and thermal constraints of the specific server deployment.
Like retrofitting versus new builds.
Right. If you have a legacy data center that you are just retrofitting for a few high-density AI racks, you might use an in-rack or a sidecar CDU. The pumping and heat exchange happens right there at the rack level. You don't need to lay extensive new piping across the entire facility floor.
But if you are building a greenfield hyperscale facility designed exclusively for AI from day one, you'd likely use larger in-row CDUs, centralizing the pumping for an entire aisle of racks to maximize efficiency and reduce the sheer number of mechanical pumps requiring maintenance.
Exactly. The modularity allows for incremental scaling, and the inclusion of the rear torque heat exchanger is a brilliant transitional technology, actually.
Oh, how so? What is a rear door heat exchanger?
It basically replaces the back panel of a standard servo cabinet with a massive liquid-filled radiator.
Wait, really? Just the whole door is a radiator?
The whole door. So for legacy servers that still use fans, the fans blow the hot exhaust air through this liquid-filled door before the air can even enter the hot aisle of the data center.
Yeah. Oh, that's clever. It neutralizes the thermal load at the exact point of exit. It's an air-to-liquid bridge.
Exactly. It captures the heat right as it leaves the rack.
Right.
But regardless of whether the heat is captured via a direct-to-chip microchannel or a rear door radiator, the thermal energy is now trapped in the liquid loop.
And the first law of thermodynamics dictates that this energy cannot be destroyed. It must be rejected.
It has to go somewhere.
Which brings us to the final and visually most structurally imposing piece of hardware in the entire schematic. The dry cooler water cooling tower.
The end of the line for the heat.
The image shows this massive multi-story outdoor structure built of industrial metal and completely topped with these enormous ventilation fans.
This is the terminal point of the thermal journey. The heat has moved from the silicon die through the copper cold plate into the PG25A coolant, through the CDU's heat exchanger, into the facility water loop, and is now piped all the way out of the building to this dry cooler.
It's essentially a giant version of the radiator at the front of your car, isn't it?
Exactly the same principle.
The hot liquid flows through extensive fin tubing, and those massive fans draw ambient atmospheric air across the fins. The heat is transferred from the liquid into the air and just blasted up into the open sky.
Yes. And the critical distinction here in the datasheet is dry cooler versus an evaporative cooling tower.
Why does that matter?
Well, evaporative towers consume millions of gallons of water, leveraging the latent heat of vaporization to cool the facility. But due to extreme water scarcity in many regions where data centers are built, water usage effectiveness, WUE, is heavily scrutinized by local governments.
Oh, right. They don't want the data center drinking all the town's water.
Exactly. So a dry cooler operates purely on sensible heat transfer. It uses zero water in the cooling process itself. It simply relies on the temperature delta between the hot fluid in the pipes and the ambient outdoor air.
Which means the efficiency of the entire multi-billion-dollar AI cluster is ultimately tethered to the weather outside.
It really is.
If it's a 110-degree day in the desert, the delta between the ambient air and the hot liquid shrinks, and those massive fans on the dry cooler have to spin at maximum RPM to reject the necessary heat.
The system is a continuous thermodynamic chain. It extends all the way from the microscopic transistors operating in nanometers all the way out to the macro atmosphere conditions outside the facility.
It is just a phenomenal chain to visualize. Let's synthesize exactly what we've uncovered in this deep dive.
It's been quite a journey.
It really has. We started with the sheer thermal violence of high heat flux on modern silicon, realizing that air cooling has fundamentally reached its physical limits.
Then we examined how Supermicro engineered the SMC PG25-A with a low kinematic viscosity, to maintain that turbulent flow through microscopic copper channels while minimizing the massive parasitic power draw of the facility's pumping infrastructure.
Right, keeping those electricity bills down. And then we delved into the chemical warfare happening at a molecular level, how the fluid must act as a lethal biocide to prevent insulating biofilms, while simultaneously deploying chemical inhibitors to build passivation layers that stop dissimilar metals from tearing each other apart through galvanic corrosion.
And we established the critical necessity of elastomer compatibility, ensuring that the polymer chains of the silicone and EPDM seals do not degrade and cause catastrophic leaks.
We also explored how leveraging a low-toxicity propylene glycol base removes the massive regulatory and logistical hurdles of scaling this technology up via those huge 1,000-liter IBC totes.
Finally, mapping the physical architecture, from the isolation barriers of the CDUs to the final heat rejection at the massive outdoor dry coolers.
So to you, listening right now, the next time you prompt an advanced AI model to generate a complex piece of code or render an image, remember that the cloud is a myth.
It's very physical.
Yes, the speed and intelligence of that response is physically dependent on the quiet, continuous, pressurized flow of highly engineered synthetic coolant racing through miles of microscopic channels, desperately fighting to keep the silicon from melting down.
And, this raises an important question as we look toward the next decade of compute.
Oh.
As AI models scale exponentially, power demands are pushing well past 100 kilowatts per rack. Single-phase liquid cooling, like the PG25-A system we explored today, relies on sensible heat transfer. The liquid gets hot, but it remains a liquid.
Right.
But as heat flux continues to condense, will we hit the hard physical limit of how much heat these synthetic liquids can carry away in a single phase? Are we approaching a horizon where we must pivot entirely to two-phase immersion cooling, intentionally boiling highly exotic engineered fluids to capture the latent heat of vaporization directly off the chip?
Wow, boiling the fluid intentionally, or even engineering completely new states of matter just to keep our data centers cool. We're rapidly approaching the absolute boundaries of traditional thermodynamics.
We really are.
The invisible mechanics keeping our digital world alive are only going to get more extreme, more exotic, and more heavily engineered. Thank you for taking this deep dive with us. Keep looking past the software to understand the heavy industrial reality of the hardware, and we will catch you next time.